Hello! In this interactivity, we're going to calculate the electromotive force. In the right-hand diagram, drag the wire upwards through the magnetic field and look at the gray shaded area inside the yellow circuit. What happens to the area as the wire moves upwards? Yes, it increases. Now let's move the wire to the bottom of the yoke and slowly raise it to the lower edge of the red magnet. Look at the gray circuit area. Does it contain any of the white lines of force? No. Let's move the wire up to the top edge of the red magnet. Does it contain any lines of force now? Yes. You already know that an electromotive force is only generated when the wire is moving, and you can see here that its area is passing through more of the lines of force of the magnetic field. Now let's move the wire up through the magnetic field faster to generate more electromotive force. Like this, for example. The flux through the circuit is changing more rapidly, so more electromotive force is being generated. If the length of wire in the magnetic field is L, and it moves upwards with a velocity v, the gray circuit area will increase by an amount LV in 1 second. If the flux density of the magnetic field is B, the flux phi through the circuit changes by an amount B multiplied by the area change, which equals to BLV in 1 second. So, the rate of change of the flux is equal to BLV. And according to Faraday's law, the induced electromotive force is equal to delta phi by delta T. This is the rate of change of flux. Hence, E is equal to BLV. This equation allows the calculation of the electromotive force induced in a conductor moving through a magnetic field of known flux density. One example of this would be the wings of an aircraft cutting lines of force as they move through the vertical component of the Earth's magnetic field. The circuit would then be an imaginary one with a horizontal area, and the wings would be thought of as conducted to a stationary meter behind the aircraft. That's all. Thanks for watching.